Welcome to CEDA-Labz. First, let's find out the answers to the questions asked in the last tutorial. First one was to design priority encoder, and here is the Verilog code for that. And here is the test bench code for the same. Another question was to design JK flip-flop with if-else statement. We will start with module name followed by port list, which is followed by port declarations. Then as always block followed by sensitivity list. As flip-flops are sequential circuits, and we are assuming it be positive edge triggered, event will occur only on positive edge of clock. Followed by begin, we will start with first condition using nested if statements. As you must know, in JK flip-flop, when both J and K are 0, next state or output, Q, holds the previous state. When J is 0 and K is 1, output is 0. And, when J is 1 and K is 0, output is 1. And, when both J and K are 1, previous state toggles. This is what it is represented here, by conditional statement, if. And finally it is terminated by AND module. And here is the test bench for the same. In initial block, we have provided all the input conditions which are to be tested. And another initial block initializes the clock, and always block generates the clock. And the last one was T flip-flop with if-else statement. And here is the code for that. Starts with the module name, port list containing Q, T, and clock. Here, Q is declared as output. But as you can see, Q is also initialized as 0. We'll explain it. Why? Then, T and clock are declared as input. Then comes the always block followed by the sensitivity list. Sensitivity list contains the positive edge of the clock as an event, as we assume it to be positive edge triggered flip-flop. As we know, T flip-flop results to previous state when T is 0. And it toggles the previous state when T is 1. And, this is what it is represented by these if statements. See, T flip-flop only toggles the previous state or holds the previous state according to the input. But, when there is no previous state, there will be nothing to be hold or toggle. That is why we initialize the output Q, otherwise simulation result will give unknown result. And test bench for T flip-flop is here. It is very much similar to the previous test bench of JK flip-flop. In initial block, inputs are provided and this block generates the clock. In this tutorial we will study about reset, and we'll see some examples of combinational and sequential logics implying the same. A reset is required to initialize a hardware design for system operation and to force a device into a known state for simulation. A reset simply changes the state of the device or design or ASIC to a user or designer-defined state. There are two types of reset. What are they? As you can guess them, they are synchronous reset and asynchronous reset. A synchronous reset signal will only affect or reset the state of the flip-flop on the active edge of the clock. The reset signal is applied as is any other input to the state machine. Synchronous reset follows the clock, that is, it will only affect the output at active edges. In any case, if reset changes in between the edges, it won't bring any change to the output. Now let's understand this concept via waveform. On the first edge of clock, reset is not yet active, so output will be same as D. On the second edge of clock, reset is low, so priority will be given to reset and output will become 0. At third edge, reset is high, so output will now follow the clock and will be high as D is high. Same is the case at fourth, fifth and sixth edge. The advantage to this type of topology is that the reset presented to all functional flip-flops is fully synchronous to the clock and will always meet the reset recovery time. Synchronous reset logic will synthesize to smaller flip-flops, particularly if the reset is gated with the logic generating the D input. But in such a case, the combinational logic gate count grows, so the overall gate count savings may not be that significant. Synchronous resets provide some filtering for the reset signal such that it is not affected by glitches, unless they occur right at the clock edge. A synchronous reset is recommended for some type of designs, where the reset is generated by a set of internal conditions, as the clock will filter the logic equation glitches between clock edges. The problem in this topology is with reset assertion. If the reset signal is not long enough to be captured at active clock edge, or the clock may be slow to capture the reset signal, it will result in failure of assertion. In such case, the design needs a pulse stretcher to guarantee that a reset pulse is wide enough to be present during the active clock edge. Another problem with synchronous resets is that the logic synthesis cannot easily distinguish the reset signal from any other data signal. So proper care has to be taken with logic synthesis, else the reset signal may take the fastest path to the flip-flop input, thereby making worst-case timing hard to meet. In some power-saving designs, the clock is gated. In such designs, only a synchronous reset will work. Faster designs that are demanding low data path timing cannot afford to have extra gates and additional net delays in the data path due to logic inserted to handle synchronous resets. Here is Verilog description of positive edge-triggered D flip-flop with active low synchronous reset. In always block, when reset is low, output will also become low. Otherwise Q will equal to the input of D flip-flop. As reset is synchronous, it will follow the clock. That is why we don't need to mention the reset in the sensitivity list. Here is the test bench for the previous code. We will generate reset in the same manner as we previously learned to generate clock. This is Verilog description of positive edge-triggered JK flip-flop with active low synchronous preset. In case of preset, output becomes 1, unlike in case of reset it becomes 0. So, if preset is low, output will become high, else it will work as a simple JK flip-flop. Here is the test bench for the same. An asynchronous reset will affect or reset the state of the flip-flop asynchronously, that is, no matter what the clock signal is. This is considered as high priority signal, and system reset happens as soon as the reset assertion is detected. Asynchronous reset doesn't follow the clock, that is, no matter what the clock signal is. If reset becomes active, it will be considered as high priority signal and output will become low. As we see, on first edge of clock, reset is not active, so output is according to the clock, that is same as D. Just after the first positive edge of the clock, reset becomes low, and as we know it is high priority signal, output also becomes low and will be low until next positive edge. At second active edge of clock, reset is high, so output will be same as D. At third edge also reset is high, so output will be according to clock and follow D. But just after third edge, reset becomes low and so becomes the output until next edge. At fourth edge, reset is still low, and that is why the output is also low until next edge. At fifth edge reset is high, that means now output will be same as D. In between fifth and sixth edge, reset again becomes low, and so the output until next clock edge. At sixth edge, reset is high, so the output is same as D. In this topology, high speeds can be achieved, as the data path is independent of reset signal. Another advantage favoring asynchronous resets is that the circuit can be reset with or without the clock present. As in synchronous reset, no workaround is required for logic synthesis. The problem with this type of reset occurs at logic assertion rather than at assertion, like in synchronous circuits. If the asynchronous reset is released, reset release or reset removal, at or near the active clock edge of a flip-flop, the output of the flip-flop could go metastable. Spurious resets can happen due to reset signal glitches. It may be concluded that both types of resets have positives and negatives, and none of them assure fail-proof design. It is Verilog description of positive edge-triggered D flip-flop with active low asynchronous reset. In contrast to synchronous reset code, sensitivity list will consist of positive edge of clock and negative edge of reset as events, because asynchronous reset does not follow the clock, and as soon as reset is low, output will also become low. Whereas, in synchronous reset code, reset was not mentioned in the sensitivity list just because reset follows the clock in that case. So, reset is also mentioned in the sensitivity list as any event occurring will depend on both clock and reset. Hence, whenever there is any event on clock or reset, only then it will enter the always block, and then it will check whether reset is low or not. If reset is low, output will become 0, else it will be equal to D. Here is the test bench for the code, which is very much similar to the test benches we used to design earlier. Starting with module name, an output declared as wire and input declared as reg. Module which is defined in the previous slide is instantiated here. And all input conditions which are to be tested are mentioned within this initial block. And this initial block initializes the clock and reset. And these always are used to generate the clock and reset respectively. And finally module is terminated. Similarly, it is Verilog code for positive edge-triggered JK flip-flop with active low asynchronous reset. Here also, as it is asynchronous, sensitivity list will have both reset and clock as events. Further, reset is active low, so when reset is low, output will be low. Or else, JK flip-flop will work accordingly. And here is the test bench. Now we will see various examples of combinational and sequential logic. Here is an example of a combinational circuit, 8:3 encoder. Output and input are declared in vector form. It is coded using case statement. In case, we will be mentioning all the input statements and output expressions. Here is the test bench. In initial block, we will mention all the inputs to be tested. Like at simulation time 0, simulator will enter the initial block and encounter first input 8-bit 00000001, for which simulator will give respective output 000. Then, it will wait for 5-time unit, as 5-time unit delay is provided between the statements. Similarly, after a 5-time unit it will encounter the second input and will give the respective output 001. Similarly, this will happen with all other cases. Here is the Verilog description of 3:8 decoder. Using case statement and bit select, form of vector we designed 3:8 decoder. It is just the opposite of the encoder. It will take 3-bit input and produce 8-bit result. And here is the test bench for the same. Here also, when simulator will encounter first input, simulator will produce the respective output 000000001. And similarly, this will happen for all other cases. Verilog description of serial and serial out register. In serial and serial out register, data will move in serially and result will be produced serially. That is why we define 3 registers for in-between shifting. Here in always block, sensitivity will have clock as event. As it is the sequential circuit, its triggering will depend on the clock pulse. Mostly, positive, edge-triggered circuits are preferred. SI is equal to R1, represents that whatever is the value of SI becomes equal to R1. That is, value of SI is shifted to R1. Similarly, R1 is shifted towards R2, R2 is shifted to R3 and finally R3's value is shifted to output SO. As we can see, here we are using the non-blocking statement. As shifting will occur simultaneously on all registers at the triggering of the clock. Here is the test bench for SISO register. We start with module and module name. Output and input declaration followed by module instantiation. Within initial block, input is provided to be shifted. And, after that clock is initialized and generated respectively. End module terminates the module definition. Here is the Verilog code for parallel in parallel out register. In parallel out register, input is provided in parallel and output is produced in parallel. All the data appear simultaneously along with all the flip-flop inputs and outputs. So, I1 equals to O1, I2 equals to O2, I3 equals to O3 and I4 equals to O4 will give result of people register. As we are using non-blocking statements, input will be shifted to output simultaneously at each trigger of clock. And here is the test bench. After module instantiation, input is provided in the initial block. At simulation time 0, it will enter the initial block. At first positive edge of clock, I1, I2, I3 and I4 values 1, 0, 1, 1 will be shifted to respective outputs O1, O2, O3, and O4. After a delay of 10 time unit, another set of input values will be shifted towards the output. As you already know, this is the clock initialization and generation method in the test bench. Here is the Verilog code for mod counter. The number of states through which the counter passes before returning to the starting state or initial state is called modulus counter. Mod 13 counter will pass through 13 states. We are initializing the value of output as for tick B1, 1, 1, 1, as there need to be some initial value to be incremented and counted. If we will not provide any initial value, this code won't work, and simulator will show unknown result, or high impedance result. So, this value will be incremented up to 13th state, via expression, y equals y plus 1 bit 1, and when y is encountered as for tick B1, 1, 1, 0, that is, 14th state, it should become for tick B0, 0, 0, 0. But it will go on to further states, that is why we need to provide this, if, block, which represents that when this 14th state is encountered, counter should move to the first state 0, 0, 0, 0. Here is the test bench for the same. As the value of y is initialized in the design block itself, we are not providing any input environment here. We are only initializing and generating clock. Here is the design block of up-down counter. An up-down counter is capable of progressing in ascending or descending order through a certain sequence. Usually up-down operation of the counter is controlled by a control signal. When the signal is high, counter goes through U sequence, that is, 0, 1, 2, 3, N. When the control signal is low, then the counter follows reverse sequence, that is, N, N1, N2, 1, 0. Here also, we are providing a control signal, named as CNTRL, so as to select in between, up function of counter and down function of counter. Here also y is initialized with an initial value, 8, bit 0. As we can see, always is triggered at the positive edge of clock. If control is 0, y will work as down counter, else it will work as up counter. And module definition is terminated with the end module keyword. Here is the test bench for the up-down counter. We (n) single quote t need to provide the input as it is initialized in the design block itself. Here we need to provide the control signal and clock signal. Here, we have provided the control signal. And this portion of code initializes and generates the clock, as you already know. This is the Verilog description of Johnson counter. The Johnson counter is a variation of a shift register counter. Johnson counters have basic counting cycles of length 2n, where n is the number of flip-flops. In Johnson counter, the complement of the output of the last flip-flop is connected back to the input of the first flip-flop. Here also, Q is initialized with a value. As we can see from the always block, value of first flip-flop, or we can say first bit shifts towards 0 bit. Similarly, second bit value is shifted towards first bit, third bit value is shifted to second bit, and complement value of 0 bit shifts towards third bit. And this is what a Johnson counter does. And here is its test bench, where we are just providing the clock generation code, as input is already initialized in the design block. Here comes the flashback time. We studied about reset design and did some examples for the same. We also did some examples of combinational and sequential circuits. You can try designing and testing of other digital circuits at your end.